Okay, let's try the problem with power transmission. So we have an automobile engine and it supplies 180 horsepower at 4,200 RPM. And what you want to find is the allowable shear stress in the drive shaft. If the allowable shear stress in the drive shaft has to be limited to 5 ksi, you got to find the minimum diameter for a solid drive shaft, the maximum inside diameter permitted for a hollow drive shaft if the outside diameter is 2 inches, and the percent savings in weight realized if the hollow shaft is used instead of the solid shaft. So this is one of those problems that's going to help you realize why a lot of shafts are hollow. Okay, so with that in mind, pause, try it out, and see what you get. Solving for diameter isn't too difficult, but this one might throw you off at first. So go forth, try it, see how it goes. 3, 2, 1, and let's head out. So first we need to use our power transmission equation. And from that we'll get what the torque is. We know that power is equal to torque times the angular velocity. And this time we're solving for the torque. So we have 180 horsepower. We have to convert that to foot-pounds per second. So we do that right here. I gave you revolutions per minute, which is not actually what we need. We need radians per second. Radians per second. So to do that, we first convert from revolutions to radian. In one revolution going all the way around, that's 360 degrees, or 2 pi radians. And so that's this conversion right here. And I convert from minutes to seconds right here. So most of this is just conversions. If you have it all in the right units, which you do if you're in SI, you don't really have to worry about this. And what you'll get is that the torque is 225 pound-foot. 225 pound-foot. Now, what's the minimum diameter for a solid drive shaft? Well, we can solve it by looking at this. Now, where did this come from? Well, remember that our shear stress is going to equal to our torque times the radius over a polar moment of inertia. What's a polar moment of inertia? Well, it's pi over 2 times the radius to the 4th power. So shear stress is going to be equal to the torque times torque over pi over 2 radius to the 3rd. And if I solve everything, I'm very, very careful, I can solve for the radius. Or in this case, I want to solve for the diameter, so they use the diameter equation instead. That's all coming from our elastic torsion formula. Okay, now if you do that, what you get is the max diameter is 1.401 inches. 1.401, sorry, not max diameter. The minimum diameter is 1.401 inches for this to work. And there would be a factor of safety, so in real life this would be even bigger. Now, how about a hollow drive shaft? Well, we go back to our elastic torsion formula, but this time, while we know the larger diameter, we don't know the smaller diameter. And that's what we're trying to solve for here. Large diameter was given to us as 2 inches. Smaller one we do not know. And so we'll do a very similar process. We plug everything in and we try to solve for this small diameter. After some rearranging, what we'll get is that the diameter would have to be, the inner diameter would have to be less than or equal to 1.8 inches. Now be very careful here. I said less than for this inner diameter because you need more material to support that stress. So if you have more material, well, that's okay. It's not going to fail. It's just becoming more and more like a solid shaft. However, if you had less material, well, it would fail. It wouldn't be able to withstand that. So be careful with how you write this. Now, it's obvious that this has a much larger diameter overall. This is 2 inches here. The other one was only 1.41. However, one was solid and the other one was hollow. So what are our weight savings in this case? Well, it would be proportional to the cross-sectional area. And so those would be, for the solid shaft, 1.541 inches squared. And for that hollow shaft, 0.5929 inches squared. So you can see already that the solid shaft uses significantly more material per unit length. And we can determine the weight savings by taking the percent difference. We get that we would save 61.3% for paying for volume of material or weight of material by switching from the solid shaft to the hollow shaft. So that's it for this problem. Thank you so very much for listening, and I'll see you all next time. Bye-bye.